Welcome to lecture number 15 of PH 4105, Advanced Mathematical Physics. We are currently discussing differential geometry, and in that, right now we are focusing on a particular kind of product that we have on the space of smooth vector fields, the so-called Lie bracket. A quick recap of what the Lie bracket is. It is a binary product which maps two smooth vector fields into a single vector field, and in fact is defined in the avatar of vector fields, where you think of a vector field as an operator acting on a function to produce another function, in the following manner. The bracket of x and y yields a vector field which, when it acts on a function f, gives you the same thing as x acting on yf minus y acting on xf. In the last lecture, we checked that this is a genuine vector field. We had also shown that it has certain very important properties. One important property which this bracket has is that it is anti-commuting. That's rather obvious from the definition. If you switch x and y, the sign changes. Another, not so obvious but quite familiar result is a Jacobi identity, which tells you that if you take the bracket of y and z and then take a bracket of that with x, this double Lie bracket, under a cyclic permutation and addition of three such terms, vanishes. That is, produces a vector field which is identically zero, or a vector field which, acting on every function, leads to the zero function. Now in today's lecture, we are going to focus on certain properties of the Lie bracket. The first one that we are going to look at is basically a property that's going to be very useful for further calculations. Say x and y are two smooth vector fields, and f, g and h are smooth functions. We are focusing on the Lie bracket of f times x with g times y. And in order to see what this Lie bracket is, we are going to make this bracket act on a third function h, another smooth function. Now by definition, this is the same as fx times gy acting on h, but gy acting on h, we had seen earlier, is just g times yh. And from that you have to subtract gy times fx acting on h, but fx acting on h is the same as the product of f and xh. Now, here you have f times x acting on a product of two functions. That is where the derivative property of vector fields come in. So when you look at this first term, it gives you essentially two terms. F is outside as a common factor, but when x goes and acts on g, it leaves yh intact, and you get one more term where g is left intact, x goes and acts on yh. So this is what you end up with. Now this is what you get from the first term. From the second term, you get minus g, y acting on f with xh left intact. Added to that, you have f left intact, y acting on xh. So now, collecting terms together, we see that we have fg, this product, multiplied by xyh here and minus yxh here. So that obviously is a Lie bracket of x with y acting on h. In addition to that, you have two more terms, this one and this one. F times xg, y, this acting on h, minus g times yf, x acting on h. And so when you take all of this together, you see that this Lie bracket of fx and gy acting on h gives you this whole thing. Each term here acts on h. So the overall vector field acts on h. Fg, Lie bracket of x and y. Added to that, you have f xg times y. Note that here f is a function, xg is also a function. So there is a product of two functions leading to a function multiplied by a vector field. So this is a vector field because it's a function and the vector field. Similarly, here you have a function, and a vector field. So this is a vector field because it is a Lie bracket of two vector fields. You are multiplying that by the product of two functions here. Here also you have product of two functions, but one in which f and xg are multiplied together, and then you multiply that by the vector field y. And here you have g and yf, which you multiply by the vector field x. Since this works for all smooth functions h, you have the following result. The Lie bracket of fx and gy is a vector field which is given by fg times the Lie bracket of x and y, to which you add f times xg times the vector field y minus g times yf times the vector field x. Now this identity is going to be pretty useful in various applications later on. In fact, we will see some applications of this in today's lecture as well. This is such an important property that I wanted to highlight this at the very beginning. One immediate application of this formula will involve the version where each of these vector fields are expressed in terms of some coordinates. So let us turn to what happens when you have coordinates. Suppose you are using a chart u, phi on your manifold, and the coordinate functions for phi are x1, x2 up to xn. We are talking of an n-dimensional manifold. Then the important thing would be that every vector field capital X, capital Y, etc. can be written down in terms of these vector fields del xi, where I runs from 1 to n. Since capital X can be written down as capital Xi del xi, and Y can also be written down as yj del xj, it stands to reason that if I know how to take the Lie bracket of del xi with del xj and use this formula, we will be able to figure out a simple expression to find out the components of the Lie bracket of x and y. When we say components, of course, we mean in this particular coordinate system. The first thing that we look at is del xi and del xj's bracket acting on some smooth function f. Of course, this is going to be del xi of del f del xj minus del xj of del xi acting on f. The form itself should immediately suggest that this has to be 0. After all, we all know that for a sufficiently smooth function, a function which has second order derivatives which are continuous, the difference of mixed partial derivatives vanish. And this exactly looks like mixed partial derivatives del xi and del xj taken in two different order. So the difference should be 0. The only catch there is, you should remember that when you say del xi acting on f, you are really not taking a partial derivative of the function f with respect to the jth coordinate. After all, f is a function of the manifold. So xi's are not even its arguments. But we all know the basic idea is this. When we do del f del xi, basically what you are doing is you are taking the proxy function f composite phi inverse, which is a function of n real variables, taking the ith partial derivative of that with respect to the ith coordinate. So this is a real valued function of n real variables, and here you are taking the partial derivative in the standard real variable sense with respect to the ith one, and then you are composing it with phi. In other words, the pullback or the proxy function for del f del xi composite phi inverse is nothing but the ith partial derivative of the proxy function for f. Now, if you use that, it's pretty easy to see that what you are going to get here when you do del xi, del f xj acting on f is the following. Del xi, let's leave that aside for the time being. This thing in here is actually del xj acting on f, the jth partial derivative of the proxy function composed with phi. Now this, of course, is the function on the manifold in itself. So let's call that gj. Remember, gj is not a function of real numbers, it's a function on the manifold. So how do you calculate its del xi? You apply composite phi inverse on that to get the proxy function for gj, and apply the ith partial derivative, the actual partial derivative with respect to that, and then compose the whole thing with phi. Now, what is Gj? Gj, remember, is nothing but dj f composite phi inverse composed with phi. So when you compose that with phi inverse, what is sitting here is nothing but the jth partial derivative of the proxy function f composite phi inverse. And that is being differentiated partially with respect to the ith component. Now, so what is in the bracket here is nothing but di dj of the proxy function composed, of course, with phi. So this is a function on the manifold. So given a point on the manifold, phi will be applied first. You will get a bunch of numbers. And then di dj f composite phi inverse will be evaluated for those numbers. Of course, this immediately tells you that del x j del x I of f is going to be dj di of f composite phi inverse, that composed with phi. And the difference of these two, which is the Lie bracket acting on f, will simply be di dj of f composite phi inverse minus dj di of f composite phi inverse. This whole difference composed with phi. But now notice that f composite phi inverse is actually a function of n real variables. It's a smooth function because that's exactly what you mean when you say that f is a smooth function on the manifold. And for this smooth function, di dj and dj di, these are genuine mixed partial derivatives. They have to be equal to each other. And therefore, this difference is 0. And since this works for all smooth functions f, we end up with this result about the Lie brackets of the coordinate basis vector fields del xi and del xj have a Lie bracket which is strictly 0. So if you are using a coordinate system and expressing any vector field in terms of components using these coordinate basis vector fields, the coordinate basis vector fields themselves have 0 Lie bracket mutually. Given this very simple result, it should be obvious that this formula can be used with x replaced by xi del xi and y replaced by yj del xj directly, where xi and yj will play the roles of f and g respectively. And this will give us a simple formula for the coordinate representation of this Lie bracket. Of course, you might object that this is a formula where you are only multiplying a vector field by a function. Whereas when you are writing this, you are not only multiplying the ith component function xi with del xi, the vector field, you are actually summing up over I as well. However, the fact that the Lie bracket distributes over summation is bilinear. It distributes over summation both in the first factor and in the second factor. It's something we had already established earlier, so that in itself should not cause any problems. All we have to do is just place, instead of x and y, xi del xi and yj del xj. Remember, you have to change the dummy index. You cannot use the same two dummy indices in the two expressions, so that you don't confuse between the two dummy indices. But after that, it's a straightforward application of the formula that we had derived before. The summation, which is implied by ij, is automatically taken care of because of the linearity property of the Lie bracket. So you have fg square bracket x comma y, that becomes xi yj del xi del xj's bracket, plus xi del xi acting on yj del xj, minus yj del xj acting on xi del xi. And notice that of these three terms, this one just drops off to 0. Because the Lie bracket of vector fields, the coordinate vector fields, are 0. So you are ending up with these two terms, and here you have xi del xi yj times del xj, and here you have a del xi at the end. And you can change both of these to del xi at the end simply by interchanging the I and j here. So this term will simply become xj del yi del small xj followed by del small xi. This and this are of course the same expression. All you have done is interchange the two dummy indices. And when you have done that, you can take both of these two terms with the del del xi common. So what you see is you end up with xj del del xj, capital Xj del del small xj, acting on yi, minus yj del del small xj, acting on xi. This is the expression for the component, the ith component of the Lie bracket. Of course, it's easy to see that this thing here is nothing but capital X. And this thing here is nothing but capital Y. So another way of looking at this is the Lie bracket has components. The ith component is given by the vector field X acting on the ith component function of Y minus the vector field Y acting on the ith component function of X. So this is the quick and easy direct way of figuring out the components of the Lie bracket. In the rest of today's lecture, I will discuss an application of the formulas that we have derived so far. In order to do that, let us consider a particular example. We are considering three specific vector fields x, y and z which have been expressed in terms of a coordinate system, the polar coordinates on 2 dimensions using r and theta as the coordinates, and these are the expressions for the components. The forms may look a bit complicated at this stage, but these are really useful vector fields for specific applications which will become clearer later perhaps. For the time being, let's just take a look at these as specific examples of vector fields where we are going to calculate the Lie bracket. So we want to calculate the xy Lie bracket. So that will have an r component and a theta component. To calculate the r component from the formula, what we need to do is calculate xyr and y acting on xr, subtract the 2. So what is xyr? The yr is nothing but this component, minus 1 plus r square cos theta. And this of course is the full x. Now, although we have been saying that these are not really partial derivatives, they are really the rth partial derivatives of the proxy functions and not of the direct functions. But notice that when we say this is the component, we are really talking about the proxy function here. So you can just treat these as ordinary derivatives. So 1 plus r square sine theta, del del r acts on this quantity. Of course, in here cosine theta comes out, in fact minus cosine theta comes out, and we are doing del del r of 1 plus r square. That's simply twice r. In the other term, 1 minus r square by r cosine theta gets multiplied by del del theta acting on this, but there of course minus 1 plus r square comes out. We are just going to do del del theta of cosine theta. It's a pretty straightforward calculation. You get 2r from here, so minus 2r into 1 plus r square sine theta cosine theta from this term. 1 minus r square into 1 plus r square, 1 minus r square 4 by r. This gives you a minus sine theta. Coupled with this minus gives you a plus. So this is basically sine theta cosine theta over r, to which you have to add 1 plus r square into 1 plus r square minus 1 plus r square into 2r, and it's very easy to do the algebra and end up with this expression. Since we are going to calculate both the components of the Lie bracket, let's also calculate xy theta while we are at it. The operator x, or the vector field x, is here. Y theta, this is the theta component of y, you just put that in. Again, the calculation is pretty straightforward, though a bit boring, and definitely not very nice to follow on the screen. It's much better if you take out pen and paper and work it out yourself. Anyway, this is a factor 1 plus r square sine theta, which is sitting here. You're going to do a derivative of this with respect to r. That's of course 1 by r, differentiated gives you minus 1 by r square, minus r, differentiated gives you minus 1. Sine theta of course stays intact. That's from the del del r term. From the other term, you do a del del theta of sine theta, so you just get a cos theta from here. And plugging them together, you get this. Very similarly, you can calculate yxr. No point really in working out every step, at least expressing every step here. they are worked out on the screen. So if you want to actually have some help, you can pause this and take it down. But again, it may be a much better idea to calculate these derivatives yourselves. Yxr, yx theta, you calculate both of them, and then you just use the basic formula. The r component is x acting on yr minus y acting on xr. So basically this minus y acting on xr, which is this, and so on, and it's pretty straightforward to see that the xyr and yxr are equal to each other. So this cancels out to give you 0. xy theta minus yx theta is actually not 0. It turns out minus 4. So you end up with minus 4 del del theta. And del del theta, remember, is our third vector field. So the Lie bracket of x and y gives you minus 4 times z. Now, this is not perhaps the most efficient method. A more efficient method would simply be to notice that if you want the ith component of vector field, any vector field, capital Xi, you apply the vector field x directly on Xi. So if you want the rth component of the Lie bracket, you apply the Lie bracket x comma y directly on r. You want the theta component, you apply it directly on the function theta, the coordinate function. So given that these are the forms of x, y and z, just repeated once again in order to help you remember. You want x bracket y acting on r, you just apply x on yr minus y on xr. This is going to give you the rth component of the Lie bracket x comma y. Now yr, that's easy. This is going to give you 1, this is going to give you 0. So that's all you get from yr. xr, again, this term is going to give you 1 plus r square sine theta into 1. The other term is going to give you 0. And then you apply x on this and y on this. Again, this is a pretty straightforward thing to apply. Of course, now you will get multiple terms because x has a del del r, which will give you non-zero term from here. Also the del del theta, which will also give you a non-zero term. Anyway, plugging all of them together, you get 2 terms from x acting on 1 plus r square cosine theta and 2 more terms from y acting on 1 plus r square sine theta. Of course, what is going to give us is something we already know. We are going to get 0 because we have already worked this out directly. Similarly, xy acting on theta is x acting on y theta minus y acting on x theta. Once again, I will not go through the entire steps, but it's a pretty straightforward bit of algebra to carry out the whole thing, and you will end up with minus 4. So you end up with the square bracket of x and y being minus 4z. Now, what about yz? I'm not going to even talk about the result, at least all the steps, but yz's Lie bracket will come out with minus x. And zx's Lie bracket, there's a third independent Lie bracket you will have, works out with minus y. So let's leave this as an exercise for all of you. What you see is if you take square brackets of any two of these vectors with each other, you are going to get another of the vectors with some function. What is important is what you get is a linear combination of the 3 vectors involved. Here it's even simpler. You only get z here, you only get x here, you only get y here. But in general, even if you had just these 3 vectors x, y and z combined linearly as a result on this side, in each of the 3 cases, you will get something which is called a closed Lie algebra. It's very easy to see what that really means. If you form a vector space by taking the span of x, y and z, that is, you take all possible linear combinations of x, y and z, what these 3 results are telling you that if you take any 2 vectors from this vector space, they will have a Lie bracket which is also a linear combination of x, y, z, so which will also be in that space. So what you have ended up with here is a finite dimensional Lie algebra spanned by 3 vector fields x, y and z. Now, Lie algebras are very, very important in physics, especially in, for example, particle physics. We are not going to talk about the Lie algebraic structure in great detail now. We may come back to that later, if I don't run out of patience by the time I get there. But the whole notion of Lie algebras is really based on the fact that the Lie brackets of vector fields can actually form a closed algebra like this. At least that's what makes Lie algebra so useful for physicists. As I said, that's not really our topic right now. We might come back to Lie algebras in the future. In the next lecture, what we are going to do is take a look at a notion that we have already seen before. Pushing vectors forward from one manifold to another using a smooth map between manifolds. And we will try to see whether we can actually extend that notion to vector fields. Can we push forward a vector field from one manifold to another using a smooth map between the manifolds? That will be our next lecture. Bye for today.